very good morning and welcome to this course on the foundations of continuum mechanics. Today, we will be continuing our discussion on the infinitesimal strain tensor, and we'll also talk about plane strain. So let us get started with this part 2 lecture on infinitesimal strain tensor. The topics for today's lecture will be as follows. So last time we talked about the interpretation of the diagonal terms of epsilon. Today we'll talk about the interpretation of the off-diagonal terms of epsilon. Then we'll talk about the interesting aspects that happen in the principal directions of epsilon. This will be followed with a discussion on the volumetric strain and its relation to the elements of epsilon. We'll briefly talk about spherical and deviatoric parts of epsilon, the same way we did it for the stress tensor. And then towards the end, we'll talk about plane strain, especially under what conditions do we see plane strain in physical scenarios. So let us get started with this lecture. So this time we will take 2 points in the neighborhood of P for the analysis. One will be called d capital X vector 1 and the other will be called d capital X vector 2. Again, if you recall from the last lecture, we had defined d small x1 dotted with a d small x2 as d capital X1 dotted with d capital X2 plus d capital X1 dot twice epsilon now dotted with a d capital X2. Now for our analysis, we will take or we choose, let's say if we choose d capital X1 perpendicular to d capital X2. Now this is our choice, so we have made this choice. And this is done for the sake of understanding of the off-diagonal terms of epsilon, as we'll see. So if I use this special case that if my d capital X1 is perpendicular to d capital X2, the above equation becomes d small x1 dotted with d small x2. Now this d capital X1 dot d capital X2 becomes a 0. So we have a d capital X1 dot twice epsilon dot d capital X2. What's happening here is, let's say these are the undeformed and deformed configurations. So we have a point P. We've chosen a point Q like this, and the point R is chosen here, so that the angle is right angle. Now if I look at the image here, I get, let's say this is my Q, I get a d small x1, and for R I get something like this, which results in d small x2. And this angle between small pq and small pr is theta. Now remember, this is small deformation, and the angles also deform in a small way. So if this is the right angle, then this angle we'll call gamma. So from here I can say gamma plus theta is pi by 2. That's how we define the angles. So gamma becomes pi by 2 minus theta. And I'll park this here for later discussion. Come back to this equation here. But let's look at this term, the left hand side. D small x1 dot d small x2. Now dot product between two vectors, that is d small x1 dot d small x2. This can be written as the magnitude d small x1 times the magnitude d small x2 times the cos of the angle between them, which in this case is the angle theta. And since theta plus gamma is pi by 2, so I can write this as cos of pi by 2 minus gamma, which becomes a sine gamma. And since gamma is small, as we just said, that it's a small deformation, so the change in the angle from pi by 2 in the undeformed configuration is to an angle which is pi by 2 minus gamma. So gamma is a small value. So if gamma is small, then we can write sine gamma is approximately equal to gamma for small gamma. So this becomes approximately equal to d small x1 d small x2 times a gamma. So let's call this 1 and let's call this 2. So from 1 and 2, what we can see is that we can write d small x1 magnitude times d small x2 magnitude times gamma is equal to d capital X1 vector dotted with a 2 epsilon dotted with a d capital X2 vector. So I'll express the gamma now, which is d capital X1 upon, let's keep the d small x1 magnitude here, dot twice epsilon dot d capital X2 upon d smallest magnitude 2. Now here what we'll do is we will take d small x1 magnitude approximately equal to d capital X1 magnitude that we have been doing, and d small x2 magnitude approximately d capital X2 magnitude. And if I do that, this becomes d capital X1 upon d capital X1 magnitude, that is the vector n hat dotted with the vector n hat. So this has given us the gamma in terms of epsilon. Now we are almost there. Let's take n1 hat equal to I1 vector hat and the vector n2 hat as I2 hat. I1 hat and I2 hat are two unit vectors in the coordinate directions in the material coordinates. So if we do that, that gives us gamma as I1 hat dot twice epsilon dot I2 hat. Now this simply becomes epsilon 1, 2. And you can see that if you expand everything in the matrix notation or you choose the initial notation. And since we're talking about taking n1 hat along I1 and n2 along I2, I'll call this gamma 1, 2. Because I'll have lots of gammas now depending on the choice of n1 hat and n2 hat. Sorry, there's a 2 here. In general, I can write gamma ij as twice epsilon ij for I not equal to j. Remember, this works when n1 hat and n2 hat are perpendicular to each other that we had assumed for the discussion. And this quantity gamma ij, which is like a measurable quantity because it's the change in angle between line elements which are at right angles to each other in the undeformed configuration. So this quantity is called the engineering shear strain. Engineering is because that is measurable, and it's called shear because it's the off diagonal terms of the strain tensor, and it denotes the change in angle between elements which are at 90 degrees to each other. So think of it, if you have a square which is basically formed by these elements, then if the angle changes slightly, it may deform to a rhombus. So this gamma or the off diagonal epsilon terms denote the shearing in elements in deformations. Sometimes we express our epsilon tensor or the infinitesimal strain tensor like this, and then the off diagonal terms are expressed in terms of gammas. So it becomes gamma 1 2 upon 2, gamma 1 3 upon 2, and so on. So we have successfully given you an understanding of the different terms of epsilon. The diagonal terms of epsilon, they denote the normal or the longitudinal strain for line elements along the coordinate directions. Similarly, the off-diagonal terms, they denote the shearing or the change in angle gamma for line elements along any two coordinate directions. Of course, the choice of coordinate system was ours, so we could have chosen x1, x2, x3 in a different way, and that will result in an epsilon which will be different. And you can get those different epsilons by doing tensor transformations by rotating the coordinate system. But as we had done earlier, that the special case where we choose our coordinate system along the principal directions of epsilon, that is called the principal coordinate system, things become simpler mathematically and more interesting. So let us see that. So in the derivation above, we had shown that gamma is n1 hat dot twice epsilon dot n2 hat, where n1 hat and n2 hat are any two perpendicular vectors in the material coordinate system. So if I choose n1 hat and n2 hat as two principal directions of epsilon, and remember principal directions are mutually perpendicular, so this also holds in that case. But things get a little interesting in the principal directions. Let us see. So what is epsilon dot n2? Well, if n2 is the principal direction of epsilon, then this by definition is epsilon 2, that's the corresponding principal value, times n2. I'll move the 2 out here, and then we have n1 dot. So epsilon 2 is just a scalar value, so this becomes twice epsilon 2, and then we have the vectors n1 dotted with and n2. And this is a 0 because n1 and n2 are mutually perpendicular to each other, so this becomes a 0. So I can conclude that the principal strain directions, they stay orthogonal under any infinitesimal deformation. Now that's very interesting. So let us say that we are working in the principal coordinate system this time, and we choose a cube element which has sides which are given by the lengths d. This is d capital X2, this is d capital X1, and this is d capital X3. So you can see this. So if this was my point P, then I basically have these three directions for my d capital X1 vector, d capital X2 vector, and d capital X3 vector. So I've taken a cube element which is oriented along my principal coordinate system in this case. And please remember that this element is very small because the sides of this are simply d capital X1, capital X2, and capital X3. Now when the deformation happens, this may get deformed to this, where the lengths in the deformed configuration now are d small x2 here, this is d small x1, and this is d small x3. So you see a cube element deforms to a cube element in the principal coordinate system because the principal strain directions stay orthogonal under any infinitesimal deformation. So the 90-degree angle between any two mutually perpendicular principal directions has to stay the same, but their lengths can change. Actually, this is a cuboidal element. I should say cuboid because the sizes of the three sides are different. So this cuboidal element can change its size. That is, it may stretch in the different principal directions differently to give a cuboidal element in the deformed configuration which may have a different volume. Now please note that the whole element may rotate as a whole because the condition is that principal strain directions stay orthogonal under any infinitesimal deformation. So the elements along these directions have to stay orthogonal. They may not have to overlap. But since all of them have to be orthogonal in the deformed configuration, the whole body may rotate overall. But since we are not interested in rigid rotations right now, and our epsilon does not contain information about rotation as well, so we'll not worry about that. So when working in the principal coordinate system, we know that the strain tensor epsilon, which we call epsilon star, looks like epsilon 1, 0, 0, 0, epsilon 2, 0, and 0, 0, epsilon 3. So in the above case, we can write d small x1 minus d capital X1 upon d capital X1, which is the longitudinal strain, that is epsilon 1. And this gives us d small x1 is 1 plus epsilon 1 times d capital X1, or in general I can write d small xi is 1 plus epsilon I times d capital Xi, where I can take values 1, 2 and 3. And remember, these dxi's are along the principal coordinate directions. So what we are doing is we are trying to express the sizes. If I go back to the figure here, these sizes dx1 in relation to d capital X1, dx2 in relation to d capital X2, and dx3 in relation to d capital X3. And this is being done to find the volume in the deformed configuration of the cuboid, which is d small x1 times d small x2 times d small x3, which using this relation here can be written as 1 plus epsilon 1 times 1 plus epsilon 2 times 1 plus epsilon 3 times d capital X1, d capital X2 and d capital X3. And the volume in the undeformed configuration is simply d capital X1, d capital X2 and d capital X3. Now we define volumetric strain as delta V upon V, where delta V is V deformed minus V undeformed. That's a change in the volume upon the initial volume, which is V undeformed. And when we do this, we will see that this comes out to be epsilon 1 plus epsilon 2 plus epsilon 3 plus, now we have product of two epsilons, epsilon 1, epsilon 2 and so on. And again remember that epsilons are small because epsilons were defined using the displacement gradient terms. So when we have a sum of these three epsilons, we can neglect all the products and the product of three epsilons because they are much smaller than the epsilons. So this can approximately be written as the sum of the three epsilon principal values, which basically is the trace of epsilon tensor. And remember, the trace is invariant. So this is epsilon II for any orientation of the coordinate axes. So delta V upon V is the volumetric strain, which is also called the dilatation. So we have shown that when our cuboidal element is oriented along the principal directions, the volumetric strain is the trace of epsilon. But the idea of the volumetric strain being equal to the trace of epsilon is not limited to our choice of the element along principal directions. In fact, this is true in general. Whatever element you take, the volumetric strain or the dilatation is equal to the trace of epsilon. We'll show that later for a general case, but right now we have shown that for a case where our cuboidal element was oriented along the principal directions, because doing the mathematics was straightforward here. Now let's move on to the next topic for today's discussion, and I'll start that discussion with a question. So the question is, what kind of epsilon will cause an equal stretching of elements in all possible directions? That is, any direction you choose, the deformation is resulting in the same stretch in that direction. What will be the mathematical nature of that epsilon? Now we have defined stretching or the longitudinal strain as n hat dot twice of epsilon dot n hat, where n hat is the direction where we have taken the d capital X vector. And we are saying that this is a constant irrespective of the n hat that you choose. And with some thought, you will realize that this means that epsilon is isotropic. That is, it has no directional preference. So this means that epsilon is isotropic, which basically means epsilon has a form which is some constant times delta ij. So in that scenario, d small x minus d capital X upon d capital X becomes twice of k. So you see, this is a constant, and therefore any direction you choose, the element would be stretching in an equal manner. And you can also check that for this type of epsilon, there will be no shear strain in any direction. Any two perpendicular n hats you choose, and you will see that this will result in a zero shearing. That is, right angles between any two perpendicular vectors will be preserved. You can check that by using the relation that gamma is in 1 hat dot epsilon dot n 2 hat. There's a 2 here. So that was the first question. And the second question, the second question is that what would epsilon look like if the dilatation is 0? And dilatation was the change in volume upon initial volume or the volumetric strain. So what kind of mathematical form of epsilon would give us a deformation where the dilatation is 0 everywhere? That means all volume elements will have the same volume in the deformed configuration. And again, we had shown that delta V upon V is the first invariant of epsilon. So if this is 0, that means that epsilon 1 plus epsilon 2 plus epsilon 3 is a 0. So the kind of epsilon that causes 0 dilatation everywhere is an epsilon whose trace is 0. And now with these two questions, you may have realized what we are heading towards. We can split any tensor into its spherical part and its deviatoric part. So the spherical part in this case is given as 1/3 of the mean normal strain, that is epsilon kk times a delta ij. It's an isotropic part of the tensor. I'll just write epsilon mean is 1/3 of epsilon kk. So this is called the mean normal strain. And the deviatoric part, eta ij, is simply epsilon ij minus the spherical part. Now you see question 1 answered this part because we said that if the stretch is the same in all directions, it's basically the spherical part that we're talking about. And question 2 answered this part because we know that by definition eta ii is a 0 because we have removed the trace from eta into alpha. So the deviatoric part is the part that gives zero dilatation. It purely results in a shear, that is change in angles, but no change in volume. Whereas the spherical part purely results in a change in volume, but no change in angles. We'll not talk anymore about the spherical and deviatoric parts because we have done enough practice in the mathematics involved with these parts. So let's move on to the next topic, which is a very interesting topic on plane strains. So we say that a plane strain situation occurs when one and only one eigenvalues of epsilon is 0. So let us say the direction 3 coincides with the principal direction of epsilon, and directions 1 and 2 can be any directions in the x1 x2 plane. So the principal directions would be somewhere here with x1 star and x2 star. So if I'm writing the strain tensor in p x1 x2 x3 plane, then epsilon 3 3 will be 0, and also epsilon 1 3 and epsilon 2 3 will be zeros. So this also means that epsilon 3 1 and epsilon 3 2 are 0 from the symmetry of epsilon. And this is something we already know because on a principal plane there is no shearing. This can be shown mathematically very easily. So the form of epsilon that we have looks like this. So this is also how we define a plane stress situation, where we said that one of the principal values of stress tensor is 0. So in this case, one of the principal strain values is 0. So in the plane stress situation, we also provided a physical feel where we said that plane stress occurs when one of the planes is unloaded. That is, there is no traction on that plane. But in the case of strains, we are talking kinematically. So we have to give you a feel in terms of some kinematic or boundary conditions that will provide the motivation for a plane strain situation. Let us take a bar which is constrained along the x2 direction. So that means the bar cannot move in the x2 direction. So with this constraint, we can see that epsilon 2 2 is a 0 because epsilon 2 2 denotes the longitudinal strain or the stretch in the x2 direction. But since the body is not allowed to move in the x2 direction, so the longitudinal strain is 0. And now let's think of an element on the x2 x3 plane such that this is d capital X vector in the 2 direction, and this is the d capital X vector in the 3 direction. And when the deformation happens, you know that epsilon 2 3 denotes the change in angle between dx2 vector and dx3 vector in this case. And if for some reason the angle had changed, This would mean that one of the points has moved more than the other. That is the only way the angle will change, but that is not possible because of the constraint in the x2 direction. So all points move to the right or the left on this x2 x3 plane in an equal amount because of the constraint. So that means that epsilon 2 3 is also 0. And with the same logic, we can say that epsilon 1 3 is also 0. So we see that for this constrained situation, we have a plane strain situation. Let us take the situation here where you have a very long bar this time. There's no constraint, but it's extremely long. And we look at some part of it. So since the bar is very long, so that means there's symmetry in terms of x3 direction. That is, any cross section, any x1, x2 cross section we take, it will behave independent of the x3 direction because the bar is extremely long. So all cross sections should behave in a similar fashion. So I can say that the displacement in the x1 direction, which is points on the bar moving in this direction, that displacement should not be a function of x3. So another way to say that is partial u1 by partial x3 is a 0. And similarly, partial u2 by partial x3 is also 0 because the displacements in the x2 direction for points on the bar or in the bar should not depend on the x3 direction because the bar is extremely long in x3 direction. So things have to be independent of that direction. And by the same idea, del u3 by del x3 should also be 0. Also, in terms of u3, u3 should not be a function of x1 or x2. Remember, u3 is a displacement in this direction along the x3 direction. Now the bar is extremely long, so all cross sections should behave in a similar fashion. So if u3, that is a displacement in the third direction, was dependent on x1 or x2, that would mean that the cross sections would start tilting or bending because some points at some x1 values will displace more in the x3 direction than other points. So if u3 is neither a function of x1, x2 or x3, that means u3 is a constant. So what was epsilon 33? Epsilon 33 was half of u3 comma 3 plus u3 comma 3, which for u3 equal to constant is going to be a 0. Similarly, epsilon 23 is defined as like this. And since we said that u2 is not a function of 3 and u3 is a constant, so this becomes 0. And in a similar fashion, epsilon 13 will also be a 0. So this is our plane strain situation for an extremely long bar because of the symmetry along the x3 direction in this case. And in this plane strain situation, where we only have epsilon 11, epsilon 22, and epsilon 12 non-zero, even they are not functions of x3 for the same reason that we have discussed here. Now next we'll talk about how to measure experimentally these strain terms. So for a plane strain situation along the x1, x2 direction, as we've been talking about, we need to find epsilon 11, epsilon 12, and epsilon 22. Now measuring epsilon 12, or we can say gamma 12 by 2, that is the engineering shear strain, is very difficult. But measuring longitudinal strain is much easier. So what we do is we use the idea of transformations and try to measure longitudinal strain in different directions and try to get epsilon 12 from that as a result. So we use something called a strain gauge for this measurement. So a strain gauge looks like a thin strip which can be stuck to a surface, and this strip has an electrical wire inside it, a very thin wire, which comes in and comes out at these two discrete points, and the wire is extremely long. As you can see, it goes through a tortuous path in this small strain gauge. So we connect this to some circuit where the resistance of the wire can be measured very accurately, and as you stick it to a physical body, it measures the longitudinal strain, that is d small x minus d capital X upon d capital X, through the change in resistance of the wire. So we have a calibrated chart given to us where the change in resistance can be mapped to a change in length of the strain gauge. We in fact use a combination of these gauges to form something called a rosette. So this is just one of those where we organize or combine three strain gauges in the delta configuration. So that's called a delta rosette. And this allows us to measure the elongation along x1, x1 prime, and x1 double prime directions. Now these strain gauges are extremely small in size because the idea is that all these three measurements give us the state of strain at a given point P. Now of course measuring on point is not possible, but we try to keep these as small as possible. So if strain gauge number A measures epsilon A, strain gauge B measures epsilon B, and strain gauge C measures epsilon C, or I should say epsilon longitudinal, then from my tensor transformation property, I know that epsilon B tensor is A epsilon A times A transpose, where A is the transformation matrix, which is obtained by a theta rotation of the axis about the x3 axis. Now the theta between x1 and x1 double prime, which denotes the strain gauge B, let's draw x1 double prime like this. So this is the theta that we're talking about, and this theta actually in this case is 120 because it's an equilateral triangle here. So all these angles are 60 degrees. So theta in this case is 120. Similarly, epsilon for the strain gauge C is A epsilon, A tilde this time, A tilde transpose, where A tilde is the transformation matrix with a theta that is equal to 60-degree rotation about the x3 axis. So with these ideas of tensor transformation, we can very easily find the epsilon 1, 2 component, that is the shear strain, by measuring longitudinal strain in different directions. We will have a problem on this delta rosette in the tutorial this week, so things will get much clearer through that problem. So this brings us to the end of this lecture. Today we started with a discussion on the off-diagonal terms of epsilon, and then towards the end we talked about the plane strain situation. Although we discussed the idea of strain rosettes for plane strain situation, but these are used for any kind of strains, again as we'll see in the tutorial through a problem. So here's a concept check problem for today. It asks us that if epsilon is a diagonal tensor for a particular choice of our coordinate system, then will it always stay diagonal? That is, if I rotate my coordinate system and try to find the epsilon at the same point P that we're talking about, will it still look diagonal, or will it have some shear components as well? So think about the idea from the perspective of principal directions of epsilon. Thank you very much, and I'll see you in the tutorial that follows next.